CLion a cross-platform IDE for C and C++. Download now.
So I'm going to introduce reinforcement learning, which got mentioned quite a few times in the keynotes. So if you don't know what it is, hopefully you'll go away with an idea of it. If you do know what it is, then you probably know about some of the ways people were learning how to set this up. Well, I'll go through a bit of history, and me being me, I'm going to use some paper bags just to illustrate the point. The reinforcement learning actually covers a huge number of techniques, but they've all got the same thing at the heart of the computer trying to learn to do something without you giving it step-by-step instructions. So it looks as though it's learnt something. I'm going to start simple. We're just going to move in one dimension, so we just go left or right to begin with. Then we're moving to 2 dimensions. One day, I'll do something that involves 3 dimensions, but that's not happening today. And we'll end up with a game of Snake, which my computer will play. I'm going to do the code in C++ because I'm also using this as an excuse to practice some C++. Other languages are available. So I did ACCU's Overload magazine. There's several on the table just down that way. Help yourself. Write for us if you want as well. I've spent most of my career as a programmer, frequently using C++ and some Python, C# and other things. And I've written 2 books, and I've got some copies of the Learn C++ by example for sale. Talk to the people on the help desk. And I've started writing a book for O'Reilly, introducing C++ and trying to explain things entry level to beginners who don't know anything about stuff is hard. But I've written this talk to try and explain reinforcement learning and how it works. And I had to learn more about it as I went. So, various ways to get in touch. Feel free to reach out, say hi. I'll share the slides on Discord afterwards, and I guess they'll be uploaded to the ACCU website too. So, reinforcement learning is a type of machine learning, so you can regard it as part of AI, whatever we mean by AI. It involves agents, which was another word we had this morning, acting in an environment. So an agent is just a process that can make choices. You can code up some rules in your agents, or you can let them discover things as they go. You can put them in a static or dynamic environment. So, for example, if instead of playing Snake, I had a grid world with an obstacle or 2, and the obstacles never moved, I can make reinforcement learning help the agent navigate its way around space. And that's useful for things like getting robots to learn how to navigate through a collapsed building and try and rescue people and things like that. Or you can have a dynamic environment. So instead of obstacles, you might have an apple that the snake can eat, and then a different apple will turn up somewhere else. So you need to do different things with the static or dynamic environments. And then you might have a situation where you can move continuously in space. So again, back to a robot moving around in physical space trying to do something. Or you might go in discrete steps, which Snake Game is doing really. It isn't at every possible point in space. It'll be a specific pixel and then add another pixel. So those are subtly different, but the same underlying principles apply to each. And what happens is the agent picks an action, like go left or right, and then it gets a reward. You can think of it as carrot or stick, or actually there's some maths behind this, as you could just give 0 if it didn't do very well and give a positive number if it does well. And you can do a lot of maths about what kind of environments you've got as to what reward schemes work best. And as it gets the reward or possibly punishment, it learns. And the theory is this mimics how we learn as well. I think the main lesson of that is if you manage to try and do something and you try and learn something, like, for example, solving the Rubik's Cube, then it's okay to give yourself a reward or a pat on the back. So if someone around you is trying to learn something, or you're trying to learn something, take time out to be kind to yourself and give yourself a pat on the back once in a while to reinforce that you are learning, and that helps you learn more. Now, loads of people, when you say AI at the moment, immediately start talking about LLMs like ChatGPT. So just a reminder, AI is a much bigger topic than this, but you do sometimes see reinforcement learning used for the fine-tuning part of LLMs. Specifically, they call that reinforcement learning from human feedback, which just means you go, thumbs down, that answer was rubbish, or thumbs up, that was better. And that will nudge it towards the kind of thing you're after. But they were explained slightly this morning. You can read more about that if you want. So we're going to start with a simple game. Whilst the game's not over, my little agent's going to pick an action, do it, see what happens. Like I said, going to start just 1D, keep it really simple. So the agent's going to start in the middle, and it can go left or right. And if it happens to end up on the right-hand side, it's going to get +1. If it happens to end up on the left-hand side, it's going to get -1. Now, I can do this at random and just see what score I get. And if you're doing AI models or stochastic modelling, it's quite good to do things without the modelling part and just try random, and that gives you a baseline. And if you can't beat random, then you're doing no worse than random, but you've probably not learnt anything. So that's a good baseline. Is anyone in Jez's talk about a small language model on Tuesday? He talked about Markov chains at that point and stochastic modelling. And this is, in essence, what's called a random walk. Because things can go +1 or -1 for right or left with equal probability, on average, you'd expect 0 to be the position. As many things that tend to go right as go left. But over time, because of things to do with the variance of what's happening in each time step, which is complicated maths, but just in essence, doing that +1 or -1. The mean's 0, but things are gradually spread out. So over time, you'd expect things to diffuse or fill the space that's available. So some of them ought to end up getting +1 and some ought to get -1. So we just do this purely at random. We're going to, I want to just pick +1 or -1. And I love all the random number facilities in C++. But the more I try and use them, the more I think there's slightly different APIs I want to use for this. So whilst the game's not over, which I checked to see whether I've gone off either end, I pick an action at random between -1 and +1 inclusive. And I've got a little rejection sampling loop there, but 0 means it's going to stay still. I don't need that bit. If I just want to pick one of 2 random numbers, there's loads of ways to do this in C++, and maybe that's a chat over a pint later on. But this works. So all it's doing is it's either going to go left or go right. And then I draw things by invoking a slightly sneaky way of clearing the screen, and I'm going to just do a string with a little plus sign, I think, to show you where it is. And just at random, it maybe goes left, maybe goes right. And like I said, eventually, some of the runs will go out one side of the bag or the other. And there we go. So that one got a +1. But we're not learning anything yet. So we've got just the random walk there. And on one run through, I did get nearly 50-50 going out of the left or out of the right, which you'd expect. And of course, there's no guarantee this will ever stop, because it could go left, right, theoretically, forever. let's start learning something now. That's our basis. We've got a loop. Whilst the game's happening, we do an action, we get a reward, but we don't do anything with it. So now, I can encode some knowledge about the domain in the agent. In effect, give it a model. For example, I could tell it to always go right as a guiding heuristic, and then it will tend to go right. But the way reinforcement learning works is you do something at random, epsilon percentage of the time. That means that the agent can explore and see what else happens if it's somewhere else. Does it get a different reward? It doesn't know what the rules of the game are. It just tries something and gets some points, plus or minus or 0. And it does this several times. And it's building up a view of the world, as it were. So we're going to run it several times now. But I've kind of cheated. I've told the agent to go right each time. So that's okay. This shows you what it's like if I'm using a model. We'll move on to no model and see if it can figure out what's happening. So more code, which nearly squashed on the screen. So we've got more randomness happening. This time we want a real number between 0 and 1 to work out whether we're going to do the random action or follow the model that we've baked in. So 1 time out of 10, we're going to do something random. And as I said, I've baked in the model. I said, just go right. If you're not doing the random thing, go right. Because we know that'll make it move out the right-hand side, and then it'll get a point. So it went right. But I told it to go right. So I've had to encode what I already know about this. And the whole point of some of these machine learning and AI things is we want our machine to learn something. So I felt like cheating. There might be some cases where you have got some kind of heuristic and you say, if you're faced between these 2 choices, tend to pick that one. So I could have done it probabilistically in there. And I'm sure you can imagine some real world situations where you might want to encode some kind of information about the environment. But that seemed like cheating and boring. Let's do something a bit more interesting. So that time, on one example run, unsurprisingly, 100 out of 100 did end up going out the right-hand side. But he was doing something random, so he could have theoretically gone out of the left, but the probability of that happening was really quite small. And I've given this a model, so let's see if it can figure this out. So this time, instead of picking the best action, my little agent's going to have a lookup table, just build up an idea of when I was in this state, and at the moment, the only state I can possibly have for my agent is where it is in that one-dimensional array. So it can be an index. If I take this action of a +1 for right or a -1 for left, the lookup value is what reward do I get? This isn't very strongly typed and there are lots of ints. Don't worry, I have a word with myself when we go to 2D, but just bear with me for now. Let's keep it simple. So we're going to have a lookup table, like a map of pair of ints to an int. And for each episode, each run of the game, the agent's going to start in the middle, maybe pick something at random, or maybe look in the lookup table and go, I'm at index 4. What should I do now? What's better? So now I've got my new function for picking a best action. So it looks up, well, if I go left, what reward did I get last time? Or if I go right, what reward did I get last time? I say last time, you can actually stack up all the rewards over all of time, or you could do a sliding window over just the last few, which is more suitable for that dynamic changing environment. But here we've got a static environment, so it doesn't really matter. Nothing's moving, nothing's changing. The agent's exploring. So if left's better, it goes left. If right's better, it goes right. And if they're equally appealing or not, then I just return 0. And I had that little while the action 0 rejection sampling. So that will then in effect pick a random move, which is like it's saying, I don't know which is best, toss a coin. Okay, let's go left. So the reward function, I've got a position into the array, which I want -1 to be a thing to say it's gone off the left edge. So those are ints. And I've got the length of the line to work out how far along it is. So if it's gone off the line length, it gets +1. But now I'm muddling up ints and unsigned ints, which is another talk in and of itself. So I shouldn't have done that. I said I was getting myself in trouble. If you do find yourself in a position where you're trying to compare ints and unsigned ints, use standard comp less. Aware of blank faces. Oh, yeah, just be careful. If it says warning, you're comparing signed and unsigned, pay attention and use something like standard comp less instead. Just pay attention to warnings. And as I said, because this is a static environment, I'll just stack up the rewards each time. So every time it goes out to the right, it gets +1 more point in the lookup table. That'll make going right more tempting. Or will it? And if it goes off the left edge, it's going to get -1, which will make it less tempting. If it's in a particular state where that's the reward it'll get if it goes left or right. We'll see why that's slightly problematic in a moment. But here it is, it's learning. I think by this point I'd trained it for quite a while. It might have been like 20 or so runs in. So it faffed around to begin with, and then it did go right. And this time I haven't told it to go right. It's built that information up by acting in the environment, and just seeing what points it got, just chuck some numbers in the map. And this time we didn't win all the time, but I didn't tell it what to do. I just said, no, good, +1, or nah, -1, or 0. And we've got 89 out of 100 wins. I can start looking at the average length of the steps before the game was over and get all kinds of other stats on this to see how quickly it's figuring it out. But it's learned something. Yes, maybe. If we look at the quality table it's built up, it's getting +1 if it's at the last possible position. So if it's at index 5 and it goes right, it gets +1. If it's at index 0 and it goes left, it gets -1. If it's in the middle, well, either side is equally unappealing, and then it does something random, which is why the demo just now, you saw it faffing about in the middle. It'd be quite nice if there was a way of making right be more tempting, no matter where on the array it was. So we've got all these zeros. We can do something about this. And at this point, I am reading a huge book and I haven't got very far through. So I'm just going to focus on one type of reinforcement learning. We've built this lookup table. And it's a type of reinforcement learning called Q learning, which dates back to 1989, which is based on some maths from the 50s. So many things in AI are based on things that are happening in the 50s at the beginning of computing. It's just, nothing changes really. We just keep relearning stuff. Now, what Q learning does, that's quality learning, it builds up a Q table, a quality table, which we were trying to do just now. But for one state, it then does the action, and it's got a next state as well, which means that when I update the current state, I can go, well, if I go right from here, I'll then be in index 5. Oh, and then I can get like 89 points. So you just give a percentage of that 89 points to position 4. So it's kind of like it percolates a percentage across to each of the other states, which attracts it in certain directions or puts it off others because the negative reward percolates just a little percentage. And that's one of the parameters you can control. I previously spoke about using cellular automata to navigate your way around space. I came out of a brilliant suggestion of how to arrange a table so everyone could get food, which no one's taken seriously. It might have been a fire hazard. Watch the YouTube. At that point, I told the agents there, little cellular automata, which part of space was more tempting. So I filled in like a field to make different places more attractive. Whereas the reinforcement learning, I'm not going to tell it anything. It's going to do stuff and figure that out. But the point of this floor field is if I've got something that I want to go out of a room and not stand in the doorway or similar, if I make it more attractive nearer the door, that's like me making it more attractive to go out the right-hand side of my one-dimensional line. But again, the reinforcement learning with the Q table can figure this out itself. So it's going to learn about this. So just to recap, when we saw my first simple, not really a proper Q table, there were numbers at the top and bottom, but everything else was just full of zeros. So now we're going to take, for each state, we're going to look at the next state as well and see the best possible thing I can do in the next state and percolate that through. There are lots and lots of words in all this AI stuff. This is called off-policy TD control. The TD means temporal difference, so it's looking at the difference between now and my next possible state. So it's only looking at like change between now and one more state. You can involve more states than this, which I might mention later on. I haven't got any examples of that. And it uses this so-called Bellman equation, which dates back to the 50s, where your Q for a state and an action, that's just the map that I'm using. You add to that the reward it gets this time, plus a discounted, a fraction of the best it can do in the next state. Now, you might not want to add all of that. You can add a learning rate. And lots of AI algos have got learning rates in. I think I set it to 1 in my code, but just something you can tweak. And that's going to percolate the end numbers into the middle. So now I've got 3 parameters going on. We had the epsilon anyway, so 10% of the time I was doing something random. Now we've got an alpha and a gamma. If that's 0, it's not going to look up the next states. And you can change it. So that helps it forget things or remember things. Like I said, you can control how much it does this. Dear, oh dear. And actually, for the Bellman equation, you can prove it can find optimal solutions to some problems. But that's some maths stuff. So this time, same as before, but we've just got the next state as well. Similar to the last code, we're updating the quality table at the bottom. But I need to find all the things that match the next state and then see what the best possible one of those is. And that, a percentage of that gets added. I haven't embedded a demo in my slides because I haven't. If I run it this time, you do see the zeros going away. So now it's still learning, but the number of steps taken is much quicker because it won't tend to do that left, right, left, right, left, right in the middle because we've percolated the numbers over. Oh, I have got a demo. That was one run after it had trained a bit. Another run took a bit longer. Don't forget, it's doing that randomness one time in 10. And now you're not seeing that dithering around in the middle because those numbers have percolated across. Just by adding a percentage of, oh, well, if I were to go right now, then it'll be even better next time. So it's kind of doing that one step ahead look, which is what the temporal difference models are about. Just having the two states. I've taught my machine to go right slightly, which is boring. We're here for snake, right? That's why we're here. We want 2 dimensions. Fran had to go back to 1 dimension. She's tried starting in 2 dimensions like this. It's too hard. Let's just go back to first principles. And actually, that applies generally when you're trying to learn something. Some of these AI models or any physics or maths modelling can start in a really complicated place. So if you find you got stuck on something, drop back a dimension, constrain the numbers, find a tiny, smaller problem to solve first, just to warm your brain up. And give yourself a reward when something works. And don't beat yourself up if something goes wrong. Just have another go. So, I mentioned my appalling code that was full of ints. If I go 2-dimensional, then I've got an x-coordinate and a y-coordinate as the place, and an action, which was an int. And this time, because of the all the Greek things, the gamma and the alpha, I've changed it to a double instead of an int. So maybe that's all right. Maybe I can make a reward type. I think I've left it at doubles in the code. But let's have some proper types here. Let's have a position and an action. And the reward function and need to match the types as well. But we can do something pretty similar, almost identical to the last implementation. We're just changing the lookup to be in 2 dimensions. And the actions, instead of just left, right, can now go up and down as well. So we're much nearer to snake. So again, this is, from here, the overall algorithm's unchanged. Just what happens in the quality and what happens in the reward changes, and the possible actions are different. And that actually means this type of reinforcement learning, and most types of reinforcement learning, can use the same algorithm, and you just change the actions and the reward table, and then you can play more than just snake. But we haven't got time for that today. And we're nowhere near snake yet. We're getting there. So I've got a position. I've got some actions. And I can go shrug if they all look equally tempting. And then it can pick a random thing. And like I said, the lookup's now doing the position and the action. And that maps to a double. Oh, and again, this is me fighting myself and losing. We're still finding the quality for this state, finding the best possible reward from the next state, and doing that alpha times the sums to update the quality table to avoid loads of zeros, just so as things that are really good over there kind of percolate through a little bit to everywhere else. Now, when I pick the best action, I want to either pick one that's brilliant, Or if I've got two that are equally good, I want them to be 50-50, or three are equally good, a third each. And again, if somebody wants to help me get better at coding and chat about my code with me over a pint, I'm sure there's a neater way of doing this. But there we go. So just what we're now doing, again, we're picking the best action 1 in 10 times, or a random action. If all of them are equally good, then it'll just pick one of those at random. If two are equally good, it'll pick one of those two only. 2D. Shaping up to look like snake. It's going to get a reward if it gets out the top of the paper bag, of course. If it crashes into the bag, no points, in fact, minus points. And I have made a very small snake go out of a paper bag. But again, it learnt to do that just from a map and some random selections. And I can look at the stats. They were much easier to look at when it was just like 5 points on a line and the edge cases. And with the states, then there were like 14 of them to look at. Well, I mean, one thing you do notice for the ups is it's more tempting to go up when it's at the top. So that's okay. Let's take this nearer snake. I'm going to put an obstacle in the bag. So that's a static environment, right? I'm going to put the obstacle in the same place. If it crashes out the sides of the bag or into the obstacle, -1 point, game over. If it goes out the top of the bag, +1 point, game over. And it'll do this several times in a loop and fill in this map or queue table. Now, I've set up the code so I could put in more than one obstacle, but I'll just show you what happens with one. Apart from that, it's very similar to last time, but now I need to check whether we've hit the obstacle or indeed any obstacle. And the only change there was that reward function of has it hit the obstacle or the edges of the bag. It went out. It avoided the obstacle. Faffing around a bit. We're exploring. There's all these AI algorithms. You need to give it a chance to explore. Because you're often trying to solve a problem where you aren't sure what's going to work and you want it to try some of the state space, but you can't enumerate all the possible things. So you just try some of them. It looks like it's trying to start avoiding the obstacle, I think. And it's out again, and it now retry. Whoops, so hard trying to avoid the obstacle, it crashed into the bottom. It doesn't know the differences, it just knows a position and the points it gets. It can't see anything. So, one obstacle, and allowing it to then run, it gradually fills in a table. Like I said, that was hard to look at. I can show this in 2D and show you what the reward is for each point in the paper bag. Where the obstacle is, the game's over at that point, so then there's no reward after that, because this is current state, next state going on. But you can see down the bottom around the edges, negative points. Round the obstacle, negative points. Top of the bag, there are some plus points. Some. And there's some that are like, nothing much happened there. That might be enough to move this to a dynamic environment. So instead of that O being an obstacle, it could eat the apple instead of obstacle using the same code and get a reward this time rather than a penalty. Then we can make the apple turn up somewhere else. Wasn't brave enough to make the snake start growing at this point. So again, the AI algorithm looks exactly the same. We've just changed the reward function. The environment knows about how the rewards work, what the game is we're playing, or the robot's trying to find people in space and rescue them or something. There's an environment. And the agent doesn't know anything about what's happening in there. It just tries stuff. So the step needs to perform the action and check whether we've eaten an apple or not, and then it needs to respawn an apple. Wonder if this is going to work. So again, this is from scratch, it's learning, so it doesn't know about the bag edges to begin with. So it might take a few goes for it to stop crashing into things. But there's the same basic algorithm. We've just changed the reward function and the action of it taking a step, because it might need to respawn an apple. Oh, go on. Yes. Not quite sure how long to leave this running for, but we've seen it. Initially, it crashed into the edge of the bag a few times, and it hasn't done that for a while. It still might, because I've still got that epsilon of like 10% it doing something random. And it's eating the apple sometimes. Oh. No, don't just give rewards. Don't have to be negative when something goes wrong. Go on. Oh, yeah, well, but I'm giving it a reward for going out of the bag as well. Come on, the apple's at the top and you get points if you go out the top as well. No. No, ate an apple, so it's learning something. It's learning something. That might be quite enough of that for now. So, because we haven't got so long left. We've got some time, but there's a typo in that slide, but never mind. Yeah, again, I can look at the state table, and that is a way of seeing whether it's got a sensible state or not. And you can see that if it goes right from the right-hand edge, the last number is minus 0.1, so that means that's bad. Whereas you can see things saying going up is good. But the information that's missing, if I just look at the Q table, is if it eats an apple, it's got a reward. Then that apple goes away and turns up somewhere else. So at this point, I'm thinking, yeah, see, now I can't see quite as much as I could when it was a fixed obstacle. I can see something. I can see it's not going out of the edge of the bag. But where was the apple? So, and this is a 5x5 bag, remember, and we're going to play snakes, so it's going to be big. I don't know, like 45 by 50 or bigger, right? So we've got 5x5 places as okay, and maybe an obstacle or an apple somewhere. And then if I do make this snake grow when it eats an apple, there might be a space, or there might be the apple, or there might be part of the snake's body. So I need to add more things to my state. And actually, now the position isn't really so important. Maybe all that matters really is, well, I can go up, down, left, right. So what is up, down, left, or right? And then I just need what character is in each of those four positions. I don't need quite so much state, which is almost like it's just looking around, just in a small window around itself to see what happens. But it might be nice to give some extra information as well and say, well, there's an O on our apple shape, in this direction. So it might be up and left or down and right, or it might be left. Won't necessarily say how far it is, just give it a hint as to, oh, and there's this weirdo thing over here. You might want to keep track of that as well. So I am still giving it things to look out for and base the state on, and I've had to decide that. And there's an extension of Q learning using neural networks that you don't need to do that for. But then I'd have to explain neural networks in calculus. So, new lookup. Character up, down, left and right, and maybe a distance horizontal and vertical for the food, which I'll just do as +1, -1 or 0, rather than giving it even more information. Just giving it a bit of a hint. So I've got a new lookup table now. The position's no longer relevant, and it isn't really. If it can see that to its left there's a bag edge, then that's good enough. So now we can play snake. So I need to respawn the apple, perhaps. Need to move, need to check if the game's over. When I move, the snake needs to grow. How do we represent the snake? Well, there's one use of a deck, right? And I've only used a deck very few times in my life, but I've seen several other people implement snake, and that's the easiest way to do it. If it eats the apple, you just add to the front. If it doesn't eat the apple, you add to the position to the front and pop the back, which will keep it the same length. Simple. Nice. So the environment's now going to take a game. And I've done a slightly leaky environment so I can render it using the SFML so it looks like a snake game. And this time, well, what rewards do you give? Then this time, I'll let it go out the bag still. I'm going to give it 2 points if it eats an apple, -2 points for game over. If it gets further away from the food, it gets -1. If it gets nearer the food, it gets +1. So I have baked in some encouragement. I haven't told it the rules. I've told it a little bit. And I can show you the stats. And of course, at this point, the state table's got huge. And that is one drawback of using the Q learning approach. If you start thinking through the number of possible states, things tend to explode really quickly. This isn't so bad for 5x5, and it does work for a larger snake game, which I'll show in a moment. So, this time, instead of just one cross for the agent moving around, I've got a deck of crosses, and I'm going to do a demo. So I've set it up so that I can save down the Q table, and then I can rerun it from the learnt state. Otherwise, you have to sit and watch it for... It wasn't so long. Just this 5x5 one took 5 minutes or so. Actually, if you think through how many states there are, like 1,000 runs isn't that many. But I can see from the Q table whether it's full of zeros or not still. And ace and apple, and grown a bit. So this is on one that's been trained, and it got 4, which is something. At one point, it did actually manage to fill up the whole grid, and I hadn't dealt with the respawning the apples properly, and no one noticed that. So I didn't notice it. What's it doing? Because when it was training, I wasn't rendering it on the screen, and it had gone, I know what to do now, but I can't put a new apple anywhere. But it's not always consistently brilliant, but it's still got that 1 in 10 random thing happening, which I could turn off, and then we see how well it does. It's doing all right. The first run, it only got 4, but it had learned something. So 18, not bad. Oh, I can't see white on a white background. So we had 5x5. In fact, I can, because I've not used the position in the Q table. I could use that same Q table for a larger grid. And the states would still be the same. There's a paper bag on one side or the other, And actually, maybe if I'm playing Snake properly, maybe I shouldn't let it go out the top. I wanted to set it up so as the paper bag was a deck as well, and if it started at the top of the bag, it could eat the whole bag. But I'm very sorry, I've not had time to get round to doing that for various reasons. But we now can play Snake. And I could use the same Q table, but I can use one that was trained on a larger grid, and it's probably going to embarrass me horribly. It still does sometimes do something a bit odd. But sometimes it does something quite cool. So I'm going to stand back and watch with you as well. I think I've made the lines quite fat, so it does overlap itself slightly, but I'm not a games programmer, like I said. Definitely playing Snake. It is going to do something stupid at some point. Because it can only see in the immediate vicinity and the direction to the food, it does get tempted to like run into itself and tie itself in knots. What would be much better would be if it could see the whole screen. And there are some implementations that do that. So, and we've got a bit of time left. I can just tell you a little bit about them. Sometimes it does that zigzaggy thing. Sometimes it goes straight and straight. But it's not keeping track of how long it is, how many steps it's taken. You could add more state, but that felt like cheating. Just telling it what's in the vicinity of the head and which direction to the apple seems good enough. Yeah, 18, not bad. And the important thing there was I got to practice doing a little bit of C++. I want to spend some time trying to tidy up the random sampling and the stochastic things I was doing. And I'd love to have a chat with somebody about neater ways of writing that code, because it barely fitted on the screen. It's doing all right. I don't think I've ever seen it get beyond 40, so I'm pretty sure we're nearly done. I should have kept some better stats on this. I've also got a variant where we can just play Snake, which might be more fun, I don't know. All it's doing is looking up. Oh, well, I'm here. I can go up, down, left, right. What's happened before? But because we've got the gamma inside that Bellman equation, that's then tending to forget things over time. But actually, in this case, because of the way I've built up the Q table, with just what it can see, it doesn't matter where it is. So I don't think the gamma's going to have much of an effect there. You idiot. It went, I want the apple, and crashed straight into itself. 36, one of its highest scores. I should have kept up running high score thing like proper old arcade games, shouldn't I? Oh, well. So, I mean, I'm pretty much done. I've prattled through that, I think. But I've showed you one type of AI. This type's really special in that. So, did anyone listen to Yutta's lightning talk where she was talking about annotated data for a lot of machine learning? Loads of things like facial recognition or spotting the difference between a cat and a dog or something like that. needs somebody to have labelled all the training data. So that the machine can go, all right, cat, if it's up a tree or whatever's going on in the computer vision stuff. Here, I didn't give my AI agent any labelled data at all. I didn't give it any data at all. And loads of people say AI and machine learning needs data. That's not true. Some types absolutely do. Yes, but reinforcement learning doesn't. It just tries things and keeps track of what's happened. So if people tell you AI needs loads of labelled data as training data, that's not always true. AI is a very broad category of algorithms. So there's subtle differences between all of them. But this one doesn't need any training data. And it can learn to solve problems by seeing what happens. So the Q-learning stuff is storing things in tables. And then I had to think about what was going to be the lookup. The value was the reward it gets, that's fine. But what do I put as the lookup key in that Q table? And you saw me try the position first and then move on to like what's up, down, left and right. If you ditch the Q table thing, and like I said, swap that out for a neural network, then you can just give inputs, for example, what colour every pixel is in the screen. And then a neural network can try and work out whether that maps somehow to the reward that might come out. So you can ditch the Q table part and swap in a neural network instead. And that's a much more general way of doing like regression or looking things up. And there are some, there tend to be Python frameworks out there. And I think DeepMind first came out with what they call deep Q learning, which is using the neural network instead of the Q table. And there's an AI gymnasium for Python that's got loads of Atari games in there. And you can use some of their trained models to play like one of about 15 different games. Or you can set one up yourself and train it yourself. But again, you saw how loads of those slides were exactly the same. It was the same algorithm. And maybe just change the Q table out. Where the deep Q learning doesn't have a map, it has a neural network instead, and that's the difference. I mentioned this being to do with Markov chains, and you can build up Markov decision processes. So anything that involves a finite state machine, you can model with this kind of thing. And actually, the machine can learn and fill in the probabilities of transitions or what the transitions actually are. So you can do it for various decision processes and it would just run it and then you say good or bad and then that fill the numbers in for the value for the lookup. Like I said, it can play lots of games. You can do other more useful things like there's an online game, the link might be in the notes, which is a compiler optimizer that plays around with the compiler optimization stuff with the reinforcement learning. So you tell it whether it's done any good or not. And I nearly wasted hours and hours on that, but then I thought I'd better get Snake happening. So yeah, you can use it for sensible things too. There we go. So there's the compiler gym link and the arcade learning environment and some notes on the deep learning stuff. And there's a YouTube video of a game of reinforcement learning how to play PacMan. You see it doing stupid things to begin with and it gradually gets the hang of it. But again, you can use that same overall algorithm for various different Atari games. I'll share the notes on Discord so you can look up the links. But reinforcement learning is slightly different to using labelled data to spot the difference between a cat and a dog, or what they call unsupervised learning that still uses data that's not labelled, but that maybe spots outliers or things that look a bit suspicious or odd. So Anyway, so that's been me, basically. I've written some books. I've a few copies of the Learn C++ by example. I'm going to kick it off playing Snake again, because it will do something really silly at some point. Go away and play with this. The AI is not magical and mystical. It's always got some kind of for loop and some randomness going on. And once you can see that bit as the main framework for looking at them all, you can implement them for silly toy examples. If you're going to start coding up a whole neural network, that's going to be a bit harder, but you probably can. And some of these things are doing some serious maths by the time you invoke neural networks, because that involves a lot of multiplying and adding up, which is why the so-called small model that got mentioned this morning needed 8 GPUs. That's a small model, but my models are even smaller. And if you didn't get to listen to Jez's small language model talk, that was really, really small, and that was written in JavaScript, so there we go.